Arch welding. Submerged welding is a common arch welding process that involves the formation of an arch between a continuously fed electrode and also the workpiece. A blanket over the flux generates a protective gas shell and also a slug which protects the weld zone. Outstanding gas is not required. The arch is submerged beneath the flux blanket and is not normally visible during the welding process. This is a well-established and extremely versatile method of welding. So the electrode may be a solid or a core wire or a strip made from sheet or sintered the material. The flux may be made by either fusing constituent to form a glassy slag or by agglomerating the constituents using a binder and also a Corning process. The chemical nature and size distribution of the flux assists our stability and determines the mechanical properties of the weld metal and the shape of the bed. Submerged-arc welding is usually operated and mechanized process. Welding current typically between 300 and 1000 amperes. The arch voltage and travel speed all affects the bit shape, depth of penetration, and chemical composition of the deposit weld metal. Since the operator cannot observe the weld full, grid lines must be placed on parameter setting and positioning of the filler wire. Although submerged arch welding is normally operated with a single wire using AC or DC current, there are a number of variants, including the use of two or more wires, adding chamfer wire to the joint prior to welding, and the use of metal powder addition. Additional productivity may be gained by feeding a small diameter non-conducting wire into leading edge of the weld pool. So this can increase the precision rate by up to 20%. These variants are used in specific situations to improve productivity through increasing the precision rate and or travel speed. Replacing the wire with a 0.5 millimeter thick strip, typically 60 millimeter wide, enables the process to be used for surfacing components. Submerged-arc welding is ideally swiped to the longitudinal and circumferential butt welds required for the manufacture of line pipe and also the pressure vessels. Welding is normally carried out in the flat position because of the high fluidity of the weld pool and molten slag and the need to maintain a flush layer. So the fillet joints may also be produced welding in either the flat or horizontal vertical position. So that's all from me. Thank you.
Next, we go to the second types of welding, which is gas metal arc welding or GMAW. It is the process of joining two or more metals of the same type by using added materials. What are the materials? Yes, these are coiled wire and shielded gas. It occurs due to the anode and cathode ion displacement on the base metal and the filler metal, causing heat energy and making both metals melt. Anyone knows what is shielding gas function? Yeah, it functions as a protective metal welding when the welding process takes place, which in order not to be contaminated from the air surrounding the weld metal environment, because wet metal is very susceptible to hydrogen diffusion, which can cause porosity defects. And the detailed explanation will be explained later. After we go to the definition of gas metal arc welding, let's take a look at the equipment. The first is welding machine. This is the main machine used for the GMAW welding process. There are many electrical components that are useful for converting electrical energy to heat. The second is gas cylinder. It serves as a reservoir for protective gases, such as carbon dioxide, argon, and helium. The third is welding gun. This is a tool for gas and wire welding to weld. If pressed and brought closer to the workpiece, the arc will light up. And then there is welding wire coils. These welding wire coils are rolled. Usually, these coils are inserted into a device called a wire feeder. In the wire feeder, there is a regulator of the cooling matter, amperage and voltage that serve to regulate the speed of the welding wire discharge. We go to the GMAW welding parameters. There are four parameters that can affect the weld result. The first is voltage, the second is ampere, the third is welding speed, and the last is shielding gas type. In GMAW, there are two types of division that's based on the type of shielding gas, namely the metal active gas or MAG welding process and the metal inert gas or MIG welding process. The MAG process is a type of GMAW welding that uses carbon dioxide shielding gas during the welding process. This process is used for low carbon steel or metal welding application. However, we cannot use this for GMAW spray transfer welding types. If we still want to use this type of spray transfer, then we must mix carbon dioxide gas with helium gas or argon gas. The MIG process is a type of a JMAW welding that uses inert or noble gases such as argon and helium. For this type of welding, it is usually used for non-metallic materials such as aluminum, stainless steel, high-nickel alloys, and several other materials. In the use of this gas can produce welds with good mechanical properties and deeper penetration when compared to the carbon dioxide shielding gas. The MIG process is a type of a JMAW welding that uses inert or noble gases such as argon and helium. For this type of welding, it is usually used for non-metallic materials such as aluminum, stainless steel, high-nickel alloys, and several other materials. In the use of this gas can produce welds with good mechanical properties and deeper penetration when compared to the carbon dioxide shielding gas. After that, we go to the disadvantage and advantage of gas metal arc welding. It is better to look at the disadvantage first rather than advantages, because as Clement Stone quote, which is to every disadvantage there is a corresponding advantage. So the disadvantage of the GMAW is the wire feeders require continuous control, and the second is burn back can occur at any time, and the third is welding porosity or small holes often occur due to the use of protective gas that is of pure quality. Advantages are: the first is high efficiency and fast processing. The second can be used for all welding positions. The third doesn't produce slack as in the case with SMAW or MMAW welding. The fourth has higher deposit amount or deposition rates than SMAW. The fifth is the GMAW welding process is very suitable for construction work, and the last is requires a little cleaning after welding.
So hello there. In this section we're going to talk about electron-beam welding. Electron-beam welding is a welding process utilizing a heat generated by a beam of high-energy electrons. The electrons strike the workpiece and their kinetic energy converts into thermal energy heating metal so that the edges of workpiece are fused and joined together forming a weld after solidification. Electron beam welding was developed by the German physicist Karl-Heinz Streichwald in 1949, who was at the time working on various electron beam applications. Steigerwald conceived and developed the first practical electron beam welding machine, which began operation in 1958. The process is carried out in a vacuum chamber at a pressure of about 0.00013 to 0.0013 Pa. Such high vacuum is required in order to prevent loss of the electrons' energy in collisions with air molecules. As the electrons impact the materials, their kinetic energy is converted to heat, which causes the metals to melt and flow together. Electron beam welding generally occurs in a vacuum as the presence of gas molecules can scatter at the beam. So this is actually the pictures of kind of overview of the process of electron beam welding. Please take a look. Now we're going to move to the advantages and disadvantages. For the advantages, we have tight continuous weld, second one is low distortion, and then narrow weld and narrow heat affected zone, and a filler metal is not required. While the disadvantages, we have expensive equipment, high production expenses, and X-ray irradiation. And this is the equipment required for doing the kind of electron beam welding, starting from the cathode, electron accelerating system, beam focusing system, weld viewing system, vacuum chamber, work traversing system, and seam tracking methods.
Now let's talk about roll bonding. Roll bonding is a solid-state cold welding process obtained through flat rolling of sheet metals. In roll bonding, two or more layers of different metal are passed through a pair of flat rollers under sufficient pressure to bond the layer. The pressure is high enough to deform the metals and reduce the combined thickness of the clad material. Roll bonding can be done at room temperature, called cold roll bonding, or at elevated temperature, called warm roll bonding. In warm roll bonding, the metals are preheated to increase their ductility and the strength of the weld. There are several parameters that affect the quality of the roll bonding product, which are the speed of the rollers, the temperature of the rolled metal before the roll bonding, the pressure exerted by the rollers, and the amount of thickness reduction. Also, as with any welding process, the surface of the metals that are to be rolled has to be clean and free of oxides. Roll bonding is most commonly used to make clad metals, also known as cladding. In cladding, we want to combine two layers of different metal plates. The base metal can be carbon steel plate, and typical clad metals are stainless steel, nickel, and copper alloys. Joining these metals is very difficult to be done in fusion welding. Thus, usually, hot roll bonding is used. The aim of the joining is to take advantage of both metals, namely the corrosion resistance of the clad metal and the great mechanical strength and thermal conductivity of the base metal. The metals undergo many steps of heating, temperature control, and rolling until they are bonded together to create clad metals with certain dimensions and thickness.
We're going to talk about ultrasonic welding. Ultrasonic welding is a welding process in which ultrasonic waves or vibration are used to generate heat for welding. Ultrasonic means that those vibrations, which have high frequency, is above the normal hearing range. Its frequency is about 20,000 to 30,000 Hz. Ultrasonic welding is a solid-state welding process where solid-state welding is a process where there is no heat added on welding. It works on the principle of energy of ultrasonic waves. Ultrasonic vibration creates a dynamic shear stress between the contact force of the two work plates. Because of local plastic deformation and heat generated due to friction between the contact surfaces, the joint formation will take place at the interface. Now let's talk about the ultrasonic welding equipments. First, the power supply. Ultrasonic welding requires high frequency and high voltage supply. The power is needed by the transducer to create vibration. Next is the transducer. This transducer is a device which can convert high frequency electric signal into high mechanical vibration, which is used in welding process, and is also connected to the welding head. The welding head is essentially a piezoelectric transducer used in welding. Third is booster and horn. The mechanical vibration supplied by the transducer is then amplified by the booster and then is then transferred to the horn. And the horn supply the amplified vibration to the welding plates. The fourth one is the fixture and clamping device. This device is essential in ultrasonic welding. It uses either electrical, hydraulic, pneumatic, or mechanical energy to hold the plates to the desired location. Now let's go on to the working process. High frequency current passes through piezoelectric transducer, where the transducer changes the high frequency electric signal into mechanical vibration. This vibration is further supplied to the booster, which amplifies its frequency, and the amplified high frequency passes through the horn, which is in contact with the welding plates. This welding creates the lap joint. One of the joint is fixed into the fixture, and the other one is in direct contact with the welding plate. These two are under fixed moderate pressure forces. Due to this vibration, oscillation shear interface occurs. It also creates a localized temperature rise due to mechanical force and friction, and this heat helps in plastic deformation and in the interface and makes a strong joint without melting the workpiece or using filler metal. Next, let's go on to the advantages of ultrasonic welding. It can be easily automated, produce high strength joint without applying external heat, process is clean and provides good surface finish after welding. Ultrasonic process is used to weld with wide variety of metal and does not develop high heat, so that there is no expel molten metal from the joint. Next, the disadvantages. It does not weld thick hard metal. So example, the thickness of the weld is about 2.5 millimeter for aluminum. Tooling cost for fixture is high and they also need a special design. And the vibration generates through transducer can damage the electrical component. Finally, let's go on to the application of ultrasonic welding. How ultrasonic welding it's used in fabrication and in nuclear reactor components. It is used in automotive industry for the key headlamps, etc. It is used in electronic industries for the switches and others, and also used in electronic industries as well. And it is a clean welding process, so it is used in medical institution to make the parts for the filter, like example masks and etc. Thank you.
Friction welding. What is friction welding? Friction welding is a welding process that uses friction to generate heat to weld the joint. This process is a solid-state weld process where the resultant joint is often as strong as the parent metal. How friction welding works? There are four main stages of friction welding process. First, the surfaces of the metal parts that will be welded are rubbed against each other at extremely high speed and pressure to generate heat. Second, the heat generated on the contact surfaces makes the surfaces of the metal parts viscous. Third, the viscous metal parts start to mix at their contact points. After the mixing level is enough, the rubbing process is stopped. Fourth, the mixed part of the metal parts cools down, and finally, the bond or weld at the joint is created. There are four main types of friction welding, which are rotary friction welding, linear friction welding, friction stir welding, and friction stir spot welding. Rotary friction welding. In the rotary friction welding, one metal part is clamped to a flywheel that rotates continuously with a very high rotating speed. Then the other metal part is pushed toward the rotating metal part with a very high compressive axial force. This will generate heat at the contact point, then it makes the joint area viscous, and finally creates a bond or weld at that joint. Linear friction welding. The working principle of linear friction welding is similar with the rotary friction welding. One metal part is also pushed toward the other metal part with high compressive axial force. Then the main difference is on how the metal parts are rubbed against each other. As the name implies, in linear welding process, the metal part moves linearly with reciprocal direction with a very high speed. Like the general process of friction welding, the speed and pressure generate a friction in the contact surfaces that results in heat generation, leading to the bonding of the metal parts. Friction stir welding. In this friction welding process, there is a tool that consists of a cylindrical solder and a profiled pin. The pin of this tool is pushed to the seam or the joint area until the shoulder of the tool rests on the surface of the metal parts. This tool rotates with a high speed continuously and moves along the seam or joint path. Again, this rotation and pressure generates heat at the joint area that leads to the parts bonding. Friction stir spot welding. The process of friction stir spot welding is similar with the process of friction stir welding. The tool also consists of a shoulder and a profile joint. The major difference is that the friction stir spot welding is rotated at a spot and not moved. The pin is plunged in the joint area. Then the pin is stirred and creates a weld. Finally, the pin is removed, leaving an exit hole in the injected spot. Now let's discuss about the advantages of friction welding compared to the other welding processes. First, it can join the similar metals. This advantage is significant since some different metals cannot be welded together with the other types of welding process. For example, copper to aluminum joints cannot be welded with most of the welding processes. But luckily, it can be welded by the friction welding process. Second, it doesn't require any external heat or flux. This makes the process easy and less messy. Third, the welding result contains minimal or no defects. Fourth, friction welding process is a very fast process. It is considered as one of the fastest welding processes, logging up to twice or even 100 times faster than the normal friction welds. Fourth, it doesn't need much surface preparation. Many conditions of surface such as machined, soft-cut, and sheared surfaces can be joined with the frictional welding process.
Now we're going to the next material, which is resistance welding. A resistance welding is joining process where metal parts are squeezed together between two weld tips. This welding method is called extremely cost-effective since no other material needed to create the bond. By the way, there are several different forms of resistance welding. They are all differ primarily by the types and shapes of weld electrodes that are used to apply the pressure during the weld process. The first form of resistance welding is resistance spot welding. Spot welding is welding process that creates welds using heat that generates by resistance to the flow of welding current. Spot welding uses the phase of geometries of welding electrodes to focus on the welding current at the desired weld location. The next is resistance seam welding. Seam welding is a subset of spot welding process that using wheel-shaped electrodes to deliver force and welding currents to the part. And then we have projection welding. Projection welding is welding process that uses heat to push the workpiece together that applied over a defined period of time. This welding process focuses on heat generation at the point of contact to generate resistance. And once the weld current generates sufficient resistance at the point of contact, the projection will collapse and then will form the weld nugget. Flash welding uses the same heat source as the other welding process. It's also similar to the projection welding, which push the workpiece together and generate resistance. However, what makes them differ is flash welding uses flashing action to create the resistance. It means it only needs a very small contact points with high densities between the workpiece to create the resistance. The last is offset welding. Like other resistance welding processes, offset welding uses heat generated by resistance to the flow of welding current. However, while similar to flash welding, in offset welding, the workpieces are already in firm contact with one another, so there are no flashing occurs. Those are all several different forms of resistant welding processes. And now we know that resistant welding machines are designed and built for a wide range of application. And here I can show you that the resistant welding application can be found in automotive, aerospace, and industrial application.